Good afternoon. Hello. Welcome to Portland 254. We have an amazing talk lined up, 3 of them in fact in this session. First up we have Writing a Transpiler by Dr. Russell Keith Magee. Clap.
Well, good morning, afternoon, as the case may be. I'm Russell Keith Magee. If you've heard my name before, it's because I've been a member of the Django core team for coming up on 12 years now, and I served on the technical review board for the everything from the 1.7 through to the 1.11 releases. However, over the last couple of years, I've been spending a lot more of my time working on the Beware project. Beware is an open source collection of tools and libraries for creating native user interfaces in Python for desktop, but also for iOS, Android, single-page web apps, and other new hardware platforms. A big part of that work to date has been getting Python running in some interesting places, most notably in the browser and on Android phones. Now, and that's what I'm going to talk about today, not about Beware specifically, but about the process of getting Python running in unusual locations. One of the many reasons that I love Python is that it's an extremely reflective language. You can use the Python language to interrogate things about the language itself as it's running. So, for example, you can define a class Bumblebee and declare an instance of that class called B, and then ask that instance for the value of an attribute name. Okay, nothing surprising there. Pretty much every programming language in the world will let you do that. But Python also lets you ask whether an object has an attribute at all. And as a critical detail, it does that based upon a string. And the value of that string can be stored in a variable, which means you can then use that variable as part of the lookup process. This ability to introspect is incredibly powerful. Languages like C, C++ don't have this capability. C imposes a hard line between the program that is running and the programming language that was used to write the program. You can't ask questions about the code that is running from inside the code. Now, and to be clear, this isn't a feature that is unique to Python. Many other languages are reflective in this way. Ruby is just as reflective as Python. JavaScript is reflective, but with an API that isn't always that helpful. Java is extremely reflective, but the reflection API is a bit messy to use, and so it tends not to get used that heavily. But Python's capabilities don't stop at introspecting the objects at runtime. They also extend to the compilation process itself. If you've been adventurous with the Python shell, you might know about 2 of those tools, the built-in methods exec and eval. Exec will take a single Python statement as a string and execute it. Give it a Python string that contains Python code, it will run that code and give you back the result. Eval is similar, but instead of taking a single statement, it takes either a block of code, so multiple statements in a string, or a code object, the pre-compiled piece of Python code, and then does the same thing. It runs that code and gives you back a result. But there are some less well-known options too, and they're part of the Python standard library. If you want to look at your code in a structured fashion, you can use the AST module, short for the abstract syntax tree. The AST is the result that the Python compiler has after the code has been parsed, but before it's been compiled. There's also PyCompile. That is a method that will take a Python file and compile it, but won't run it. So you'll get a PYC file, the compiled output of the Python compiler, but the code itself won't have been executed. This can be useful if the code that you're talking about has side effects, or you just want to manipulate the bytecode without actually running it. Once the code has been compiled, the dis module, short for disassemble, will let you pull apart the compiled bytecode and see what was produced. Okay, but why would you care? Why do you need to use these modules? Well, the good news is, as a day-to-day Python user, you probably don't. But there are times when you do need to dig into internals and work out what exactly is going on. And you can use these tools to transform Python into something else. And that's what we're going to look at today. How to use these modules, in particular dis and AST, to transform Python code so that it can run in new environments. Which brings me back to my original problem. I love Python. Python's great. That's not the problem. The problem is that sometimes you can't run Python. Or at least you can't run CPython. And that distinction between CPython and Python is an important one. Python, the language, is an abstract thing. It's a specification of syntax and semantics that describes how a particular sequence of human-readable bytes will be interpreted by a computer to make the computer do something interesting. Then there's the Python, the interpreter, that you install and run. When you tell someone to go to the Python website and download the installer, you're not strictly talking about Python. You're almost certainly talking about CPython, which is the de facto reference implementation of the Python language specification. This separation between implementation and specification is valuable because it means that CPython isn't the only way that that Python code can be interpreted. There are features of Python as experienced by end users that are features of CPython, not the language itself. The GIL is the classic example of that. The global interpreter lock, the perpetual bane of Python performance discussions, is not an inherent feature of CPython. It's a feature of the specific implementation of Python, CPython, and because of the way it's implemented, it needs to have a GIL, or if Larry Hastings gets away, maybe it doesn't. Other implementations of the Python language specification, like Jython, PyPy, Stackless, they don't have a GIL because of the way they're implemented. And if you're going to try and get Python code running somewhere else, then you're going to need a Python interpreter that supports that platform. One way, not the only way, mind, but one way is transpilation. The word transpilation comes from transforming compiler, a compiler that transforms code from one form to another form. This usually means source code to source code. Depending upon what platform you're targeting, there may be other options. Okay, so what does this mean in practice? We have some Python code. We want to run that code without using CPython. So let's take an example. As a case study, here's a simple Python function. It sings you a little song. It's a for loop over a descending range with a couple of print statements on every loop. If we put all this code into example.py and then we run python example.py, Python will parse and compile this code into bytecode. Bytecode is a little bit like high-level assembly language. It's a stack-based machine with basic primitives for pushing and popping values onto a stack and so on. There's about 150 bytecode instructions the CPython virtual machine understands, and the Python executable is essentially just a program for running and evaluating those 150 instructions. Python then gives you the tools to inspect that bytecode. The dis module, which I mentioned earlier, allows you to disassemble any function or class or whatever into its bytecode representation. So if you run dis over our sing method, what do you get? Well, you get the raw bytecode instructions. This is the human-readable interpretation of what is contained in the PYC file. It's a sequence of assembly-like instructions. We start by configuring a loop, setting the instruction offset for the bounds of the loop down to offset 47. We load a global symbol called range. That's the range built-in function. We load 3 constants onto the stack. We load 100, 0, and -1. Those are the 3 arguments that are going to go into range. And then we invoke the function. The call function we're going to call has 3 positional arguments. They're the 3 most recent values that have been loaded onto the stack. And the function we're going to call is the one before that. Line 15, although the offset 15, is effectively the call range 100, 0, -1. That pushes the result back onto the stack, which is an iterator. So we ask for the evaluation of that iterator, and then start the actual for loop, and so on and so on. Okay, so what can we do with that? Well, option 1, we can implement a CPython bytecode machine. And while that might seem like a daunting prospect, it's actually not that difficult. CPython bytecode, like I said earlier, only about 150 instructions or so, a good chunk of which are basic mathematical primitives, just addition, subtraction, multiplication, division. So re-implementing those doesn't actually take that much code. How much code? Well, a full Python interpreter written in Python is the subject of Chapter 12, Volume 4 of Architecture of Open Source. In that chapter, Alison Kapter presents a full implementation of a Python virtual machine written in pure Python. And as the subtitle suggests, it's less than 500 lines of code. The biggest complication is that CPython makes no guarantees of compatibility in bytecode versions. Between 3.4, 3.5, 3.6, there have been several major changes in bytecode formats and interpretations. But you can stay on top of these. It's not a major problem, just kind of an annoyance. And this is what Batavia does. Batavia is an implementation of the CPython virtual machine written in JavaScript. And because it's written in JavaScript, it can run in the browser. If you've ever seen projects like MAME, the Multiple Arcade Machine Emulator, or Archive.org's Console Living Room, these are doing exactly the same thing. They take the cartridge images of classic games and provide an in-software implementation of the hardware that used to run them, the Atari 2600, Commodore 64, whatever else. Now, this isn't transforming anything. It's just providing an alternative interpreter for the same compiled binary code you've always had. Okay, so what else can you do? Well, you can try transforming code at the compiled binary level. Let's go back to our example program. We've written it in Python here, but we could have written it in many other languages, like, for example, Java. Okay, so here's some Java interpretation of exactly the same program. We compile this with Java-C, and we'll get a sing.class file. And if we look into that class file, what do we see? Well, you see bytecode. Now, okay, it's different bytecode to Python, but it is a stack-based bytecode language, and there are a lot of commonalities. You push any byte integer onto the stack, store it as a variable, load it again, jump to the end of a loop on a condition, load a symbol, allocate new objects, invoke a method. So if they're both bytecode and they're both stack-based, can you convert from one to the other? Well, yeah, you can. It's not necessarily easy, though. For simple programs like this one, it's fairly straightforward. A push is a push. You just got to account for the change in language. But when you get beyond really, really simple programs, it's not quite as simple as an instruction-by-instruction conversion. We take something like exceptions, for example. Python has an explicit set of bytecode operations for handling exceptions and block context. Java bytecode doesn't have instructions for exceptions. What it has is metadata attached to the code itself to give the description of the context in which certain exceptions may be handled. Excuse me. It's not ambiguous. If you have nested loops in your Python code, it can sometimes be difficult to tell the difference between the end of an inner loop and the end of an outer loop. It's not ambiguous, it's just kind of difficult to reverse engineer if you're trying to work out the equivalent code. After all, bytecode is the output of a compilation process, and sometimes compilers will actually optimize things to remove stuff that's just getting in the way of a fast code path. So as a result of that optimization, you lose some of the context around code that would make it easier to reverse engineer. What you really need to be able to see is the code as it's being compiled. And that's what the AST module is for. The usage, just as simple as this: import the module, call parse. And what you get back is the root of the parse tree. You give it a Python file, a module, and it gives you back a module. Now, that module itself is not useful code. It isn't the same module object you get from actually importing. It's an in-memory representation of the parsed code. And as the name abstract syntax tree suggests, it's a tree. The module is a single child, the root node, the body. The body is a series of statements. In our case, a single statement, a function definition. That function definition has some attributes: the name of the function, the arguments to the function, and it also has a body, the statements of that function, and so on. And you can traverse this tree and respond to the various nodes of that tree and the attributes of the nodes of the tree as needed. To make it even easier to walk the tree, the AST module provides an implementation of the classic visitor pattern. So you can hook into the parsing process and use that as a trigger to stimulate activity. What activity you stimulate depends upon what sort of transpiler you're trying to build. Now, the simplest kind is a straight code-to-code transpiler. This code here is a painfully naive start of a version that would output JavaScript, but hopefully it demonstrates the idea. Whenever you see a function declaration, a function def, you output as a string to the console the JavaScript function declaration, and then the arguments, the open brace, the processing of the child nodes, and then the closing brace. When you see a for loop, visit for, you start outputting a JavaScript for statement. You ask the loop for the name of the loop variable, interrogate the start values, the end conditions, and so on. Now, like I said, this implementation is very, very naive. It ignores function return values. It doesn't handle keyword arguments. It admits most of the detail in converting an iterator-based for into a C-style for. It also outputs the console rather than to a file. I've skipped over the part where we convert a Python-style iterator into a C-style for loop. Implementing those details is left as an exercise for the reader. But there's also a deeper problem here. Let's take this as a really simple example. These two code snippets are cosmetically the same, modulo a language translation. First one is written in JavaScript, call scope test, x equal x times y, call scope test and print the output. Second one's written in Python. A function called scope test does x equals x times y, call scope test, print the output. What happens when you run them? What does the JavaScript console output? It outputs 30. What about the Python? Well, it outputs unbound local error because the local variable x has been referenced before assignment. Why? Because JavaScript language scoping rules put the x into global scope. Python scoping rules means x can be accessed for reading, but not for modification. Now, okay, sure. For the pedants, if you used an ES6 let in the JavaScript version or a global in the Python version, you'd get output parity. This is an intentionally simple example to illustrate a point. The problem gets a whole lot more complex when you have structures like closures involved. And what's the native ES6 representation of a yield statement? What about yield from? If you have to deal with those problems, the generated JavaScript code ends up being a lot more complex than just a straight, walk the tree and output a slightly different variation of the language. If you don't handle those sort of problems, you end up with something like CoffeeScript, a language that is Python-like, but not actually Python. And that may not matter, it depends on your use case. But you have to be clear about what it is you're trying to achieve with your compiled output. Okay, so what other options do you have? Well, you can also transpile directly to your final representation. For example, Java is a compiled language. It compiles to Java bytecode. We saw an example of Java bytecode earlier. The advantage of bytecode is that it's just a set of primitives. There aren't any complex scoping rules here. It's just the same sort of basic push onto stack, pop off of stack, invoke function as primitive mechanisms. Java will compile takes Java source code and compiles to those primitives. But so can any other language. A class file, at the end of the day, is just bytes on disk. And as long as you can generate bytes on disk in the right order, you can produce a Java virtual machine compatible class file. To do this, we retask our visitor to produce bytecode rather than source code. Effectively, what you end up doing is a tree transformation, transforming an AST of Python code to an AST of Java bytecode. That is, a representation of a Java class file, and then as a final step, outputting that Java class file AST as Java class file AST as bytes on disk. The structure of a Java class file is extraordinarily well documented, and it's very easy to break down into a tree-like structure consisting of a symbol table and then class metadata, then individual functions, each of which have their own metadata descriptions. Something like add Java function pretty much maps directly to a node inside the Java class file tree. And if you make the visitor track context, then you can establish whether you're inside a class or inside a global context. And based upon that context, you can make decisions like whether or not to set the static flag on the Java method. But what about something like add Java for? Well, a for loop is really just a sequence of instructions, some preamble and some postamble that sets up the conditions of the loop, some internal code, which is itself a sequence of instructions. But in order to do that, you need some additional tooling. If we go back to the bytecode version of our program, there are three things worth noting. The first is the declaration of max stack. The JVM requires you to pre-declare how deep your stack is going to be as a result of execution. If your stack is too large, you end up wasting memory. If it's too small, the JVM will crash because it hasn't allocated enough memory. Secondly, there's max locals. The JVM requires you to declare how many variables your stack-based virtual machine is going to use. Python stores and retrieves variables by name. Java uses an index. iStore1 means store the current top of the stack as variable 1. So you need to track how many variables are being used and what number you've allocated to which Python variable, because if your Python code loads a symbol, you need to know which Java local to load. Lastly, the instruction at offset 4, if GE34. Now that's a comparison of the value at the top of the stack, and if it's greater than or equal to 0, jump forward 34 bytes of instructions. Not to instruction 34, forward 34 instructions. To instruction 38, which is 34 more than the current instruction. So, when you're processing the body content of your loop, you need to keep track of the size of each instruction you add, because you need to post-process to set the offset of the FGE instruction. So it's not just a tree representation of a class file we're building here. We need to have a bunch of accounting in place to track Python's variable usage, the size of generated code, and so on. Okay, so we set up that tracking. What about statements like yield? How do you handle those? Java, the language, doesn't have the concept of yielding, and Java, the bytecode, is just a set of primitives. Well, what you need to do is build the logic for a yield statement using the primitives that you have available. But because you're dealing with primitives, you don't have to think about what Java source code would produce this bytecode. You can just write bytecode that does what you need it to. And what's a yield? Well, it's a function that knows how to resume itself midway. So here, on the left, we've got a simple example of a generator called Jenny, which yields, with two yield statements in it. On the right is a sort of a Python-y, pseudocode-y kind of interpretation of that function. It's not just a function, it's a full class. It's stateful. When you initially invoke the generator in Python, that's instantiating an instance of the generator. And it stores the arguments that were used to invoke the generator. When you call next to iterate onto the next value of the generator, it's a normal method on the generator object. Now that generator has state, so it can track which yield point it was previously at, and the generator, if the generator's been yielded before, it can jump forward, use a goto effectively, to jump forward to that line of code. Now, this code doesn't make any sense in Java, doesn't make any sense in bytecode, but in Python, but it's completely legal Java bytecode, because Java bytecode has a primitive to jump. Move the instruction forward X bytes. If there's no current yield point, we just keep executing the code as normal. Set a value, start the loop, and then we yield. A yield is three things. First, we save the current state of the generator. The Python AST code.
Another sector of the building has reported a fire alarm condition. Management is investigating. Please remain calm where you are. Please wait for further instructions.
I didn't do it, it wasn't me. I mean, I knew this was hot content, but still. Oh, is that what? Yeah, okay. Right. Okay, all right. Can I work through this, or is this going to be a problem? We keep going. All right. On the next invocation, where were we? We save the current state of the generator. The Python AST code knows which variables are in use. It knows which registers they should be in. And we can explicitly copy all of those values out of local storage and into the state of the generator. Second, we can set the current yield point. We just enumerate those. The first one you come across in the code is yield point 1. Now, I've represented the first two of these as function calls in pseudocode, but you can't actually do a function call there. And as soon as you call a function, the locals for that function pass out of scope. So this actually has to be done inline in the method, in the generator function, as a series of calls. At last, we just return the value that we want to yield. On the subsequent invocation, we have a current yield point, so we jump directly to that point of the code, restore the state, again, reload all the values of the local variables from the generator's store back into locals. Again, this needs to be done inline so that you're loading the generator's local scope. And there you have it. Generators implemented in a language that doesn't support them. A full AST visitor has a total of 54 entry points, corresponding to all the node types and language entry points that occur in Python code. Some of them, like yield, are quite complex, but many of them aren't. Visit pass, for example, doesn't take very much implementation. And some of them, things like list expressions, dictionary expressions, set expressions, share a lot of commonalities. So the task of implementing a visitor that can visit all Python programs isn't as daunting as it might seem. This AST to bytecode transpilation process is exactly what Voc does. Voc is a transpiler that converts Python source code to Java bytecode. The upshot of this is that when you define a class in Python and compile it with Voc, it is a Java class file. It's not some approximation or a wrapper, it's indistinguishable from Java. And as a result, you can write Python code that talks directly to Java APIs, Swing, Android, whatever it is you need. And you can write Android applications in Python. As an interesting historical footnote, Voc actually started trying to do the bytecode to bytecode transformation that I described earlier on. It's now an AST to bytecode transformation. Make of that what you will. It's also potentially a future direction for Batavia. The emergence of ASM.js and WASM means that it might be worth looking at doing the direct AST to bytecode transpilation for JavaScript, bypassing the JavaScript language entirely, targeting the VM, or as close to the VM as you can get. But Python isn't just a language specification. Python comes batteries included. It has a standard library to help you get stuff done. The CPython standard library is made up of two parts. There's a pure Python part and a part that's written in C. If you've got a library written in Python, it doesn't matter if it's part of the standard library or part of PyPI. You can just take that, compile it, and use it wholesale. It's Python code, so it compiles as Python code and runs the same as everything else. We can compile it to bytecode, run it through our new virtual machine, cross-compile it to a new target platform, and just run it on our re-implemented Python, whatever it is you happen to need. But the bits that are written in C are a little bit more complicated. There are a couple of reasons why a module might be written in C. First, there are occasions where what we're doing is talking directly to system services. If you're going to make a POSIX system call, well, you're going to need to have a method to call a C method to implement that call. But there are also modules that are implemented as C modules because they're a wrapper around some library whose implementation is C. bzip2, for example, is a compression library. The reference implementation is written in C. Sure, you could rewrite it, but why would you? Just implement it with libbz2. Lastly, there are parts of the standard library that are implemented in C for performance reasons. For example, the decimal module used to be implemented in pure Python. For performance reasons, it was ported to C in Python 3.5. And that's great for CPython as an implementation of Python. Nobody's going to complain about more performance. But if you're looking at CPython as a reference implementation, it's a bit annoying because it means it's something you're going to have to re-implement natively. What's really needed is a reference standard library, an implementation of the Python standard library that's written entirely in pure Python, except for a clearly detailed minimal interface to system services. And that's what Ouroboros is. For those not up on your mythology, Ouroboros is the Greek symbol of a snake eating its own tail. Ouroboros is very much a work in progress, but it's an important part of the whole puzzle of Batavia and VOC and so on, if we're going to make it easy to bring Python to as many platforms as possible. Now, if you're interested in something other than JavaScript or Java as a target platform, hopefully I've given you enough detail to start down the part of writing your own transpiler. If you do want to target JavaScript or Java, which I'm using for the demos today, the good news is you don't have to build your own transpiler from scratch. Ouroboros, along with Batavia and VOC, are part of the Beware project. And you can use those to deploy your Python code to the browser or to Android, respectively. Details of those projects and more can be found on pyb.org. And if you're interested in writing user-facing apps in Python, targeting mobile phones and browsers, I'd like to draw your attention in particular to two parts of the website. First off, Beware is an open source project, and we're actively looking for contributors of all levels of experience. Even if you've never contributed to open source before, you think you haven't got enough skill, you're wrong, we want you. We'll find something for you to do. Really easy to get started. We have tutorials and walkthroughs for the contribution process, and we've got an open offer to mentor anybody who wants to get involved. I will be in booth 103 for the rest of today. If you haven't already come by and pledged your allegiance to Team Green, go Team Green. You've still got time, and thanks to Kogan, you could win one of 4 Kogan Agora 4G Android phones. I'll also be around, along with a couple other members of the Beware team, until the end of the sprints, working on Beware, thanks to Revolution Systems. We've also got a stash of challenge coins, which we give to anybody who contributes to the project, thanks to GitHub. We also have a second challenge coin for yak herders, people who help other people commit patches. Thanks to Sticker Mule, we have plenty of ISO-compliant hex stickers, and Travis CI has given us plenty of capacity for running our CI testing during the sprints. So if you're owed a coin, or you'd like to get one, or you want stickers, come grab me, we can have a chat. Second point is an appeal to you, the Python community. To date, Beware development has been mostly a volunteer effort. That seriously constrains the rate of development. I'm also looking for a job, but I think we can solve 2 problems at once. For US $10 a month, you can join the Beware project as a member. If I can find 1,000 people in the Python community who want these tools, are willing to support their development financially, I can start working on Beware full time. If I can find more than 1,000 people, then we can start to do some social good as well. For some time, I've had an open offer to mentor anybody who wants to get involved in the open source contribution process. I'd like to take the next step and start to hire and pay some junior developers, giving those developers the opportunity to advance their skills and their public profile, and prioritize giving that opportunity to people from underrepresented demographics. It's still very early days for Beware. Financial support means faster progress. Best of all, we can all get these great tools to use Python code in all the various places we might want to use Python without having to give up on our open source ideals. I'm excited for what the future holds for Beware. I hope you'll join me on this journey. And with that, I don't think we have time for questions because apparently the building's on fire. So thank you very much.
The building is not on fire.
Yes.
It's okay. We now have a 10-minute changeover. That was the all clear, so off to your next sessions.